Hello, my name is Jordan Richardson, and this is for CSE 546, Introduction to Machine Learning. This is homework number 3. So in this project, we use a variety of classification algorithms to a movie reviews data set. These are the different classification algorithms we use. These are some of the requirements we had for the assignment, and I will show you some of my code. So this is the first model that we run KNN. So I kind of actually follow the same process pretty much throughout this code. The reason, through all these models actually, the reason for that is because of the data. So it's actually already pre-processed. It's been one hot encoded, so it's just a bunch of zeros and ones. Just for example, there's no columns, no headers. So we load the data in. Sure, it's a 1D array. I convert them to NumPy just to make things faster. We do L2 normalization for cosine. We define the parameters, and then we also do Euclidean distance metric along with cosine. So this is the function. This will evaluate Euclidean no normalization and cosine with L2 normalization. We'll convert the results to data frames. It will then find the best result for each metric automatically, print those, and then depending on what the best metric is, it'll actually select either cosine with L2 or Euclidean with none, train a final model, and then predict on the test data. So then we have a actual versus predicted, which is the misclassified samples. And then we plot both normalization methods just to compare those. And then we get all the training and testing values and plot those as well. So that way we can identify on the final model a normalization method if there's been any underfitting or overfitting. And I kind of just basically carried a lot of this through to the other ones. So the second one is multi-naive. So you can see it's very similar. The only things that changed between some of them were different scaling methods. Here you can see that my code is running. This is actually a previous one, and this is actually multinomial here. So these are just a few examples of my code. Hi again, this is Jordan, and this is homework 3, and this is the presentation for this assignment. So here's our agenda. First, we're going to have an introduction, just my thoughts about the assignment, and more explained. And then we'll go through each of the models more in depth and over my results. So for the project, we were applying various classification algorithms to a movie reviews data set, which I actually covered a little bit. The classification methods provided to us were KNN, multinomial naive Bayes, random forest, and gradient boosted regression trees. The data this time was already pre-processed and one hot encoded, which means we only have data of zeros and ones. There's not even headers. We also needed to identify cases of underfitting and overfitting for each of our models, along with comparing the accuracy, explainability, and time of each method. My initial thoughts for this assignment, I did find it a little bit more difficult than the prior assignments, but some of that actually just may be my own fault. I'm transitioning into full-time currently. So I've been busy with that, along with capstone and another class, and I just didn't happen to dedicate as much time to this assignment as I did prior ones, but I will for future assignments. So our first model is the KNN classifier. For this model, I actually had more trouble with it than other assignments, which I know we've used it quite a bit now. And I saw that you've also posted a Blackboard that other students were having trouble. But it was really just that I found myself tripped up a little bit with the distance metrics and adding normalization methods, or a variety of them, to the data. I did still arrive at good results for really all of my models after debugging. So for this model, I compared no normalization, Euclidean distance, and L2 normalization utilizing cosine distance metric. So you can see that cosine performed a lot better than Euclidean just in general. Over here, it's almost as much as 20% in some areas. I also think that KNN performed quite slow on this data. Took over 10 minutes to run this program. However, you can see that after moving forward with cosine and comparing training and testing data afterwards for underfitting and overfitting purposes, the graph looks pretty interesting. So at the beginning, it's pretty massively overfitting. It's 100% on the training, but it's only at 65-ish on the test. It's still overfitting here, and even at 11. But then right here at 15 to 21, it hits that sweet spot, and then it actually stays pretty stable from around 50 to 100. So at a decimal value, I found a 91 to be the best parameter for KNN. 79.74% accuracy and a test accuracy of 79.87. We had a total of 5,033 misclassified samples. And then now we have the multinomial naive Bayes classifier. I was able to bring over quite a bit from KNN, change a few things, and get the ball rolling. I found this model to be my favorite. It's very fast and immediately gave pretty decent results. It only takes a minute or two to run my entire model, along with the analysis. No normalization was what I determined to be the best for this model. Alpha of 0.1 was the best parameter. We had 190 misclassified samples. What I did find interesting about this model is that regardless of normalization, I tested 3 methods here. They all really start to drop off right around the singles place, going into the second and third place numerically. But since no normalization is at the top above all of them, obviously you're going to want to choose from one of these points that have the highest accuracy. So I found the best alpha to be 0.1, which I believe is that one. And then here you can also see that it's not overfitting or underfitting here really anywhere. It might look like a gap that's pretty big in the graph, but if you look closely, it's actually all in a decimal range of the hundreds. So next we have the random forest classifier. I had to change quite a bit of my code for this model, but I was still able to keep most of the process similar, especially the analysis, etc. I don't think I got the best solution on this model. It was just taking a lot of time testing different parameters. So I actually stopped this one for a while and came back to it. But I found normalization methods did not make any difference for this model whatsoever. They actually were exactly the same when they came out, regardless of what the normalization was. I tested n at a variety of values and found that 5 was the best only due to factors of overfitting and underfitting. This was the third slowest so far, KNN being second and multinomial being first. So here's the graph just kind of showing that none of the normalization methods made any difference. It's like exactly the same. The only difference you see here is just that the shapes are hanging out behind each other. The most important word for this model was 250. And I found 5 to be the best in value at 74%. It's slightly overfitting just a little, but it's still performing better than data down here at n equals 1 when it's less than 70%. I tried to minimize the gap between these, but just results in general weren't great for this model. I had 5,030 misclassified samples. Lastly, we have the gradient boosted regression tree classifier. So for this model, I actually did go ahead and use a parameter grid search just to see how it performed versus running it myself and manually making changes like I was with random forest. Right here are the best parameters that I got. And while this did take a massive amount of time to run, it enabled me to finish the assignment sooner. And then once I did find the best parameters, I removed this because normalization did not matter. And I just set the parameters and moved forward. I was able to get 84.19 accuracy on test, and I had 3,953 misclassified samples. For this model, I've decided that 50 is the best parameter. This is mainly just due to factors of overfitting. It's gradually getting closer to 100% of the training data, and this is not improving drastically. 79 was the most important word, and as far as I could tell, there was nothing that was underfitting. So here's the explainability and accuracy section for this project. Multinomial naive Bayes was the fastest. It's one of the more explainable models that calculates probabilities on the frequency of words. KNN was the second fastest. We've covered this before, but it's pretty unexplainable. Random forest had the lowest accuracy, and speed was third. But its explainability is more complex, but it does offer feature importance, which allows you to kind of organize your code or data better. Gradient boosted regression tree, speed was the lowest, but accuracy was actually the highest. Feature importance can also be calculated just like random forest, but individual predictions can be hard to make sense of just due to the interactions between the trees. This is it for homework 3. Thank you.